Okay, I'm going to go ahead and start. Okay. I'm going to share my screen. Okay, we're going to take a look at nuclear magnetic resonance spectroscopy today. This will overlap both lecture and lab.
Dr. Trump, I was curious, why is it we jumped from 11 to 14 and now we're going back to 13?
No particular reason.
Okay, I was just curious.
Okay, so 14 was actually my goal. So we're ahead of schedule. So the next 4 lectures, okay, that would be 2 this week and then 2 after a break, will be review, and then the last Friday will be your 3rd exam. And then you'll have a final exam during finals week. It'll be the day that's scheduled, but you'll have a wider time window than what's indicated. Okay, nuclear magnetic resonance spectroscopy. Okay, despite the term nuclear, this doesn't involve radioactivity, or it usually doesn't. There was a true story of a research university that received a grant to set up a nuclear magnetic resonance spectroscopy facility, and then a government inspector showed up to demand where they were going to demand a plan for what they were going to do with all the nuclear waste. Well, the humor in that is there's no nuclear waste that's being generated. Right, nuclear magnetic resonance spectroscopy, also called NMR, is the most powerful tool available for organic structure determination. In fact, this will give us a lot more information actually than infrared. Okay, there's a wide variety of nuclei that can be studied. These are just a few of them. These are some of the most common. But more than 90%, I would say, involves NMR of protons, or hydrogen-1. Carbon-13 is of interest to organic chemists. Nitrogen-15 is an isotope of nitrogen that's not very abundant. Most nitrogen is nitrogen-14. I have done a couple of fluorine-19 NMRs. Fluorine exists as one stable isotope in nature, and that's 19. And then phosphorus-31 is often of interest to biochemists, since DNA and RNA contain phosphodiester groups, and there are other important molecules like ADP and ATP that contain phosphorus and similar molecules. Let's look at nuclear spin first. A nucleus with an odd number of protons, that is an odd atomic number, or an odd mass number has a nuclear spin. Okay, that's what these all have in common. Okay, notice carbon-12 is not listed. Okay, you can't use carbon-12 to do NMR because it does not have a net nuclear spin. The spinning charged nucleus generates a magnetic field called a magnetic moment. Okay, so this actually behaves like a little bar magnet when it spins. Okay, in the NMR experiment, an external magnetic field, which is designated V sub 0, is applied to a small bar magnet, and then it twists the bar magnet to align it with the external field. Okay, there's two possible arrangements. The bar magnet can be aligned with the magnetic field, or it can be opposed. The aligned arrangement is lower energy and more stable, whereas the opposed is higher energy and less stable. Okay, when we're talking about protons, and most of our discussion will be about protons, or actually any nucleus with a magnetic moment. The alpha spin state is the one that is aligned with the field, the external field, and the beta spin state is the one that is opposed. So there's just two spin states, aligned or opposed. Okay, in the absence of an external magnetic field, nuclei are oriented in all directions, and there's no energy difference between or among these. But when an external field is applied, then we have this separation into the alpha spin and beta spin states. Okay, what this indicates is that the higher the external field, the greater the separation in energy between these two spin states. Right, here's the equation. The energy difference is directly proportional to the magnetic field strength. Okay, energy is equal to h nu, and this is equal to gamma h field strength divided by 2 pi. And gamma is what's called the gyromagnetic ratio, and it is a constant for each nucleus. Okay, so for hydrogen 1, it has this value. Okay, for a different nucleus like carbon-13, gamma would have a different value. Okay, in a 14,092 Gauss field, a 60 megahertz photon is required to flip a proton. Okay, this involves low energy in the radio frequency region of the spectrum. Right, a nucleus is in resonance when it is irradiated with radio frequency photons having energy equal to the energy difference between the spin states. Okay, so these spin states are quantized. Okay, so this has to absorb just the right amount of energy in order to flip the spin state. Okay, under these conditions, a proton in the alpha spin state can absorb a photon and flip to the beta spin state. Okay, any other energy other than this particular amount would not cause a flip in the spin state. Okay, if all protons absorb the same amount of energy in a given magnetic field, not much information could be obtained. This would just be a curiosity. But the fact that protons are surrounded by electrons, and these electrons shield them from the external field. And different hydrogens in different environments will have different degrees of shielding. Okay, and that's the whole point here. Okay, so circulating electrons create an induced magnetic field that opposes the external magnetic field. Right, so we have an induced circulation of the electron cloud. Okay, this can be thought of like having a wire loop in the magnetic field. Okay, if we had a naked proton, no electrons, at 300 megahertz, and a magnetic field of 70,459 Gauss, we would have absorption, we would have resonance, we'd have spin flipping. But for a shielded proton, okay, notice here the magnetic field is the same, the RF energy is the same, but there's no absorption. Okay, we can, in order to get a match, we can either increase the strength of the magnetic field or we can go to a higher radio frequency. Okay, in this case, we just had to increase the strength of the field a little bit, going from 70,458 to 70,459. Okay, then we had a match and then we had absorption. Okay, so protons in a molecule exist in different chemical environments, and so their electrons offer different degrees of shielding. Okay, in methanol, the 3 protons on the carbon are all equivalent, but they're different from the one that's on the oxygen. The hydroxyl proton is not shielded as much as the methyl protons. Okay, that's because oxygen is pulling electrons strongly away from the hydrogen. So that means that hydrogen has a thin electron cloud, meaning it's less shielded, and it will absorb at a lower field. Okay, compared to this hydrogen, these will absorb at a higher field. Their protons have a greater amount of electron shielding. Okay, so that proton is de-shielded somewhat by the presence of that electromagnetic oxygen atom. Okay, there's basically 4 things that we're looking at in a proton NMR spectrum. And the first is the number of signals. Right, the number of signals shows us how many different kinds of protons are present. And of course, in methanol, sorry, not methane, methanol, there would be 2 kinds of protons. Okay, we'll also look at the location of signals. Okay, on the spectrum along the x-axis, what's their position? The position along the x-axis tells how shielded or de-shielded they are. We'll look at the intensity of each signal. Okay, that will correspond to the number of protons giving rise to that signal. We'll also look at signal splitting, which will show the number of protons on adjacent atoms. Okay, this is a very crude diagram. This is the old style of 40 years ago or so. Okay, this part of it is pretty much the same. We have a sample tube, which is placed down in this probe. And these sample probes are prepared to a very high degree of precision and tolerance. They have to be perfectly straight, perfectly round, very uniform wall thickness. Okay, because they're spun around at 60 times per second. Okay, so it's placed in a magnetic field. There are some variations in how the magnet is generated. The NMR instrument that we have has a permanent magnet. There's an RF transmitter, okay, which supplies the radio frequency signal. And when there's absorption, then we see a peak. Right, this is different from our instrument. We have a 90 megahertz instrument which uses a permanent magnet. This is one that uses a supercooled superconducting magnet. The magnet's at the center of this great big tank. This is surrounded by liquid helium, and that liquid helium is surrounded by a jacket of liquid nitrogen. Liquid helium is just 4 degrees above absolute zero, 4 Kelvin. Okay, you can generate a more powerful magnetic field with this superconducting type instrument. I took an NMR class several years ago during the summer at the University of Texas at Austin, and they had just gotten a new 500 megahertz NMR. It was roped off with all kinds of warning signs to keep out strong magnetic fields. And during the night, a telephone repairman came in, and he had stepped over the rope. He was curious as to what this was. And the magnet was so strong that they found him the next morning. He was stuck to the magnet. He couldn't get his tool belt undone.
How'd they get him off?
They actually had to shut down the magnet. They had to shut down the instrument.
That's crazy.
He was embarrassed, but otherwise all right. All right, so here is methanol. And we have 2 sets of peaks here, or 2 peaks, I should say. This larger one corresponds to the CH3, and this smaller one corresponds to the one that's shown in pink here. Okay, and then we'll explain this little one down here. That's a reference that's been added to the sample. Okay, so this direction to the left is called downfield, to the right is called upfield. And so downfield and deshielded go in the same direction. Okay, so that little peak down here at the end, okay, that is a compound called tetramethylsilane, which has been added. It is an internal standard. It's to make sure that your instrument is lined up correctly. And by definition, the TMS signal is 0 ppm. Okay, so this is, we want to make sure the TMS signal is set at 0, and then everything else is lined up correctly. Okay, most organic protons will absorb downfield or to the left of TMS. So that makes it a good choice as a reference. These protons on the methyl groups are more shielded than most other protons in organic compounds. Carbon is more electronegative than silicon, so it's pulling electrons away from the silicon, which will produce a high electron density around these hydrogens. Okay, all 12 of these are equivalent. Tetramethylsilane is chemically inert. It's volatile. It's easily removed from the sample. Okay, we use, on the x-axis, we use a unit called chemical shift, and that's in parts per million. And the advantage of this is it doesn't matter what our frequency is in megahertz for our spectrometer. So it's independent of what kind of spectrometer we use. And the most common is to use what's called the delta scale. Okay, 40 or 50 years ago, they used something called the tau scale, which went in the opposite direction. Okay, and so here are a couple of different instruments, and the point of this is that, again, the main point here is that these both use the delta scale. Okay, so our instrument is 90 megahertz, and there are instruments that go all the way up to 900 or 1,000 megahertz. Okay, the higher the radio frequency, the larger the magnet you need. Okay, one of the factors that can cause a variation in chemical shift, okay, again, this is the position that the peaks appear along the x-axis, is electronegativity. Okay, if we consider the chemical shift of these hydrogens on the CH3, okay, if X is fluorine, okay, then the signal appears at 4.3. If it's oxygen, 3.4. And you can see as the electronegativity gets less, the peaks appear more upfield. Okay, if we have more electronegative atoms attached to the same carbon, we'll see an increase in chemical shift. Okay, so here's methane. Its chemical shift is 0.2. Chloromethane is 3.0. Dichloromethane, or methylene chloride, is 5.3, and then chloroform, trichloromethane, is 7.2. Chloroform is often used as a solvent. Okay, we replace its hydrogen with a deuterium. Okay, the farther protons are away from an electronegative atom, the less effect it has. Okay, so here's 1-bromobutane, and the alpha hydrogens will show up at about 3.4. The beta hydrogens 1.7, gamma hydrogens 1.3, and notice with butane, that's the same value. Okay, so the effect of the bromine is completely gone by the time you get to the third carbon and the fourth carbon. Okay, so the effect drops off very quickly with distance. Okay. Okay, like IR, NMR allows us to determine the functional group based on chemical shift, but we can also get a lot more information as well. Okay, so here we have an alkane, okay, with no other functional groups present, just a saturated hydrocarbon. You can see that the chemical shifts will show up on average around 1. Okay, those protons on a methyl alpha to a carbonyl, okay, they're going to show up about 2.1. Acetyletic hydrogens, about 2.5. And then if we have an electronegative element, either a halogen or an oxygen, on the same carbon as the protons, then we see a chemical shift of about 3 to 4. Okay, a vinyl, okay, hydrogen directly attached to an alkene, about 5 to 6. There is some variation that can go a little beyond 6 or a little below 5. Okay, and then if we go from vinyl to allylic, okay, that's now 1 carbon removed from the alkene. Okay, then the approximate chemical shift is about 1.7. Okay, hydrogens attached directly to a benzene ring. Okay, these are considerably downfield, around 7.2. And then benzylic protons, again, 1 carbon removed from the benzene ring, about 2.3. Aldehyde and carboxylic acid protons are going to be way downfield, 9 to 10 for aldehydes, about 10 to 12 for carboxylic acids. Okay, and then OH and NH protons tend to be highly variable. They can vary depending on concentration, temperature, hydrogen bonding. There are several factors that can affect their chemical shift. Okay, here's an explanation of why some of these functional groups have chemical shifts in regions where they do. Okay, if we start out with phenyl protons, we have an induced magnetic field or ring current produced from the aromatic ring. And this opposes the applied magnetic field along the axis of the ring. Protons in the region where the induced field reinforces the applied field are de-shielded, and they're going to appear at lower fields, okay, usually between 7 and 8. Okay, so these protons are going to be in a de-shielded region. Okay, so that's a similar situation with alkenes. Okay, here's the nodal plane. The hydrogens are in a de-shielded region. Pi electrons generate a magnetic field that opposes the magnetic field in the middle of the molecule. Okay, although the CC triple bond of an alkyne is strongly electron withdrawing, the three-dimensional geometry is such that shielding tends to counteract the chemical shift, and so the acetyletic proton lies along the axis. And so whereas alkene protons would show up about 4 to 6, acetyletic protons are more shielded, and they'll show up about 2.5. Right, for an aldehyde proton, we've got 2 things going on. Okay, there's the strong dipole moment of the carbonyl. Okay, that's de-shielding. And also, the proton is in a de-shielded region of space. Okay, we call that anisotropy. Okay, and that means that the magnetic field varies depending on geometry, varies depending on position in space. Okay, so up here, this is a shielded region, but then in the nodal plane of the pi bond, this is a de-shielded region. Okay, OH and NH signals are highly variable, as I mentioned. They're relatively acidic protons, and the chemical shift will depend on concentration. Hydrogen bonding is more pronounced in concentrated solutions. That will tend to deshield the protons. And then we have another thing going on, that's proton exchanges between molecules. And these will tend to make the peaks broader. Right, so here is acetic acid. Okay, the methyl protons will show up here at about 2.1. And the carboxylic acid proton, okay, you can see it's a broad signal. Okay, and this, where it says offset 2 ppm, okay, that means that it's off the scale. So it's showing up on the graph at 9.8. So if we add 2 to that, this will show up at 11.8. This is an artifact of the old chart printers. Nowadays, we can, on the computer screen, we can widen the spectral window so as to include everything. Right, we alluded to this earlier with methanol, and that is the number of distinct types of protons will correspond to the number of signals. Okay, so here we have methyl tert-butyl ether, and the methyl protons are distinct and different from the tert-butyl protons. And since there's 9 of these, okay, we'll have a larger peak than for the methyl that's color-coded in green here. Okay, these 9 are all equivalent. They'll produce just one signal. These are all equivalent. They produce just one signal. Okay, another example, this is called tert-butyl acetoacetate. Okay, we have another tert-butyl group. Okay, that's this big peak down here. We have a peak here that for these methyl protons alpha to the ketone. And then we've got the CH2 that's between the 2 carbonyls. Okay, so these are going to be more deshielded because they're next to 2 carbonyls. So you can see they're more downfield or to the left. Okay, predict the chemical shifts. Okay, the CH3 on acetic acid, that should be around 2.1. And then the carboxylic acid proton is going to be around 10 to 12. Okay, here we have 1-chloropropane. The alpha hydrogen should show up at about 3.5. It says experimentally 3.7. The the protons B are 1 carbon removed. They're predicted to be about 1.7. They're actually experimentally 1.8. And then C protons show up at about 1. So they're feeling very little influence from the chlorine. Okay, here we have an alkene. Okay, so B and C protons are directly attached to the alkene, so they should show up between about 4 and 6, and it says experimentally 5.8, 4.9. And then the tert-butyl, okay, which are more removed from the alkene, they're going to show up about 1. Okay, intensity of signals. Okay, the more protons we have in a group, okay, the more intense the signal will be. Okay, so here again is methyl tert-butyl ether. And you can see that the tert-butyl protons give a signal that's taller than for the methyl protons. Strictly speaking, it's not the height of the peak, but it is the area under the peak, which in calculus that's called the integral. Okay, and NMR instruments can perform integrations. And so we'll have integrals in a ratio of 9:3 or 3:1 for these two peaks. Okay, that's important information. Okay, the integral. Okay, that can help us narrow down the possible structures. Right, non-equivalent protons on adjacent carbons have magnetic fields that may align with or oppose the external field. Okay, this magnetic coupling causes the proton to absorb slightly downfield when the external field is reinforced, slightly upfield when the external field is opposed. All possibilities exist, so the signal is split. This is called spin-spin splitting. Okay, it might seem to make things more complicated, but it actually provides some really useful information. Right, so here's the compound 1,1,2-tribromoethane. Okay, we have two different sets of protons. We have this one on the carbon with the two bromines. We have these two hydrogens on a carbon with one bromine. And these are designated as A and B. Okay, the A proton should be more downfield, okay, because of the two bromines, and it is. And it's showing up at about 5.7. These are showing up at about 4.1, it looks like. And notice that both of these are split. Okay, let's consider this set of two lines, which we call a doublet first. Okay, the chemical shift of these protons are going to be affected by what this one proton on the next carbon over is doing. Okay, if that proton is aligned, okay, then we get a slightly different signal than if that proton is opposed. Okay, let's consider the other signal here. This is split into three. Okay, so we're looking at the A proton. The A proton is going to be affected by what the B protons are doing. Okay, this time there's two of the B protons, and the possibilities are that both could be aligned, both could be opposed, or we could have one aligned and one opposed. Okay, since there are two possible ways of having one aligned and one opposed, we can see that the middle peak is about twice as tall as the two outside peaks. And so it's twice as likely to have one aligned and one opposed as to have both aligned, for example. Okay, and that's called a triplet. Okay, so the n+1 rule says that if a signal is split by n equivalent protons, it will be split into n+1 peaks. Okay, so if there are no adjacent hydrogens. Okay, 0 plus 1 would be 1. Okay, and that's what we would have back here with something like this. Okay, this methyl is a singlet. Okay, it has no adjacent hydrogens, so 0 plus 1 is 1 peak. If there's 1 adjacent hydrogens, then we'll see a doublet. If there's 2, then we'll see a triplet, 3 a quartet, and so on. Okay, we can approximate the relative heights of these peaks using what's called Pascal's triangle. Okay, in Pascal's triangle, each number is the sum of the 2 above it. Right, so for a doublet, the 2 peaks are of about equal height. For a triplet, the peak in the middle will be about twice as high as the 2 outers. And then for a quartet, these will be in the ratio of about 1 to 3 to 3 to 1. All right, equivalent protons do not split each other. Protons bonded to the same carbon will split each other if they are non-equivalent. And protons on adjacent carbons normally will split each other if they're non-equivalent. And protons that are separated by 4 or more bonds will not split each other. Okay, so here we have long-range coupling bonding to adjacent carbons, 3 bonds between the protons. And this is the most common case. When hydrogen atoms are 4 bonds or more apart, spin-spin splitting normally is not observed. When it does occur, it's called long-range coupling. Right, so here we have ethylbenzene. And okay, protons on a benzene ring will show up between 7 and 8. That's what these are. And then we have a CH2, which is here. Okay, it is more downfield because it's closer to the benzene ring. And then we have the methyl, which is the most upfield. Okay, by the N+1 rule, these methyl hydrogens have 2 neighbors. So by the N+1 rule, they would be split into 3 peaks, and that's what we see. The CH2, okay, there's no hydrogen here. The CH2 has 3 neighbors. So 3 plus 1 would be 4 lines. So the CH2 gives rise to a quartet. Okay, and then this is what we call a multiplet. Okay, these 5 benzene hydrogens are all very similar. There's a lot of splitting going on. Okay, this proton is split by this one is split by these 2, this one is split by these 2. And so we have a pretty complex pattern. Okay, I don't know how well you can see it, but there's some light blue numbers. Okay, these are the integrals. Okay, and they correspond to the relative number of hydrogens in that group. Okay, so 5 hydrogens for the benzene, 2 for the CH2, and then 3 for the CH3. Okay, if 2 multiplets or 2 split signals are split by each other, they will lean toward each other. Okay, notice this is not exactly symmetric. Okay, so a very common splitting pattern is a triplet and quartet. Okay, that's an ethyl group. Another common splitting pattern is a doublet and a septet. Okay, that is an isopropyl group. Okay, so here is methyl isopropyl ketone. All right, the methyl has no neighbors. So 0 plus 1 is 1. Okay, that's a single peak right here. Okay, this CH is split into 7 peaks by these 6 neighbors. Okay, so we have a septet. These two CH3s are equivalent, and they are both split by this one neighbor into 2 lines. Okay, so a doublet septet. Okay, we're running short on time, so I'm going to go ahead and stop here. And I'm going to record the remainder of this chapter. I also have another video in which I'll demonstrate solving some spectral problems. Okay, and then Wednesday and Friday, I'm planning to have some practice problems from previous chapters. Okay, so I'm going to go ahead and stop here since we're running short on time.